Hello everyone, welcome to IIT and GATE classes. This is lecture 9 on operating system, and in this lecture we are going to resume our producer consumer problem. If you try to remember what I have said in the previous class, by the way this slide has been copied from the previous lecture only. So what I have told you, producer is a process which is producing some item, consumer is a process which is consuming those items. Okay, so three cases are there. Consumer processes, consumer speed is more than producer, then no problem, consumer will have to wait. Consumer and producer both have same speed, so no problem, no one will wait. But when producer speed is more than consumer, then obviously consumer will be overwhelmed. Okay, so producer is the rate at which producer is producing item is more than the rate at which consumer is consuming item. So obviously consumer will be overwhelmed. Okay, yes, so for example producer is producing items, say 10 items per second, and consumer can consume only 5 items per second. So obviously 5 items are lagged behind, na? That is the problem. So what will be the solution? Solution will be producer will produce item and store them in buffer. From that buffer, consumer will consume those items. So obviously we need a buffer. So now the question arises, what is the size of the buffer? Okay, so buffer size may be infinite or finite. Infinite, that is not possible to implement, but finite, again there will be problem. What will be the problem? When buffer is full, then producer has to wait. Okay, when buffer is full, then producer will have to wait. Okay, yes, and they should. And another problem is they should not access the buffer at the same time, because when producer has produced item and it is accessing the buffer at the same time, consumer will come, then it will get problem. Don't worry, I will tell you how problem will be created and all, but you just try to remember this thing. And it is by common sense also, when producer is accessing the buffer, then consumer should not access the buffer, because it is a shared resource, no? So that will create problem for us. Okay, anyhow, please take snapshot. I will jump to the next slide, and now I will show you the code of this producer consumer problem. And by the way, we are also calling it as bounded buffer problem. Why? Because the size of the buffer is bounded. Okay, size of the buffer is bounded. Okay, yes, because infinite buffer that is not allowed. Yes, take snapshot. I will jump to the next slide. Yes, so now I'm going to show you the code. Don't worry about the syntax and all. It is Pascal language, and Pascal language is not in our any competitive exam syllabus. So you will, by common sense, you will get the hint that what exactly they are saying. Okay, so the first line is saying shared data type item. So item, I have told you now, producer is producing items. So these are, so we have created a data type called item. Okay, and where buffer array 0 to n minus 1 of item. So array which can take value from 0 to n minus 1, and it is of item type. Okay, so yes, so producer is producing items and consumer is consuming those items. Now, so I have created item data type, and now I am saying I have created array of this item, and array of this item will be nothing but your buffer. I think you have got it. Okay, next is in and out. These are the two pointers which can take value from 0 to n minus 1. Counter is a variable which can take value from 0 to n. Actually, in and out are also variables. I'm just considering them as pointer. Why? Please hold with me. I will tell you after 2-3 minutes. Okay, so just imagine in and out are pointers which are which can take values from 0 to n minus 1. Counter which can take value from 0 to n. Okay, and in, out, and counter, these are the three variables. Sorry, these are initialized by 0. In and out are pointers, and counter is a variable, and all are initialized by 0. And now producer process, I have shown you the code. So let me tell you few things, then you will be able to understand this code. Okay, so first of all, the very basic thing is, so a buffer which we are imagining, or that is a circular queue. Buffer is a circular queue. Why circular queue? I think you have idea from data structure algorithm. Linear queue, if we implement linear queue by array, then obviously time complexity will be high now, or you can say we have to shift the elements. I think you already know. Let me tell you. See, for example, we have imagined a linear queue. Okay, so front end will point to the you can say from where we will delete the elements. Okay, and rear end will point to the location from where we will insert the elements. Okay, yes, so you can imagine like this. So this is a, here is a person who is standing and he is giving the tickets to the persons, and these are the queue of the persons. So obviously first ticket will be given to this. So because for this person, this is the front end, na? So deletion will be done from the front end and insertion will be done at the rear end. So now imagine that the array size is 1, 2, 3, 4, 5. So only 5 length array we have defined. Okay, and front end is at the start location, and rear end is at the end. So now, for example, this person has given ticket to it, or you can say we have deleted this element from the array. So then front end will point to this location. Okay, and then for example we have deleted this element also, so front end will be pointing here. So when front end is here, see this, when front end is at this location, first two locations are empty. but still we cannot insert element here. Why we cannot insert? Because insertion is done at the rear end, and rear end is at the end of the array already. So we cannot extend the end. That is the problem. Okay, so the only solution is you have to shift these three elements from here to here, and then you can insert and so on. I think you have studied that in data structure. Just to revise you, I have told you. Okay, so now the best solution is from this. If rear end can come at here, then our problem will be solved. So insertion will be done at here and here. Okay, so now there is no need of you can say shifting elements and all, and that is the perfect sense of the circular queue. Why? Because you can imagine like this. This is a circle, na? We are getting circle type of thing. Are you getting it? We are getting a circle type of thing. That's why we call it as a circular queue. I think you have got it. Actually, circular queue is nothing. See, in memory, we cannot have a circular queue. Memory is not circular. Memory is linear only. So it's just our imagination, and we are imagining it just like a circular thing. Okay. So the basic idea is we should take circular queue only. Okay, because it will help a lot. Shifting of elements will not be done and so on. Okay, and circular queue has various you can say applications. If you have studied networking, then in TCP you have studied circular buffer and so on. Okay, so everywhere circular queue is used or circular buffer is used. Okay, so because it will you can say time complexity will be you can say very less, or it is much more efficient than linear implementation. Okay, so that's why we are taking a circular queue. So now let's take an example. So this is a circular queue. Okay. Yes. So how many elements are there? So let me label that also. Element number 1, 2, 3, 4, and 5. Okay, 5. You can say 5 locations. And by the way, we have defined array 0 to n minus 1. Na? So I should not do it like this. I should label from 0 to n minus 1. Whatever they are saying, we will do it. So 0, 1, 2, 3, and 4. Okay. So 5 elements from we are counting from 0. They have I am not saying they are the code is saying, that's why I'm just trying to show you how code is working and all. So 0 to n minus 1. So same here, 0 to 4. We have done it. Okay. So now what we will see this. So initially, see this in and out and counter all are 0. So in and out. Okay. So I think you have got it. Now I have told you in and out are the pointers which can take value from 0 to n minus 1. Counter is a variable which can take value from 0 to n. And initially in, out, and counter are 0. Okay. Initially all are 0. So in, out. In is here, out is here. Both are at 0. Okay, and counter is 0. So let me tell you, counter 0 means buffer is empty. Counter 0 means buffer is empty. Okay, and counter, see, it can take value up to n. Na? So when counter is n, counter is equal to n, buffer is full. Buffer is full. I think you have got it. Okay, yes. So producer, when producer will produce item, it will increase the counter. And when consumer will consume the item, then it will decrease the counter. I think you have got it. By the way, please, I should not tell all these things. First, let me explain in and out, and then I will explain the code. You will get more clarity. Okay. So forget about counter. You just consider it here, in and out. So these are the two variables, or we can say these are more precisely, these are the two pointers, and which are initially pointing to 0 location. Yes, that is our 0 location. Yes. So now in and out both are at 0 location. So now what I will say, I will simply say producer has produced some item. When producer has produced some item, so it will be placed here. So let us suppose item 1 is placed by producer and it is here. So out will be keep on pointing to this location, but in will come here. Okay, yes. So now I2 is produced, item 2 is produced by producer. So out I2 will be placed here and in will point to the next location. So are you getting it? So wherever insertion is done at in. Okay, so wherever the in is pointing at that location, insertion is done by the producer. Okay, so for example, I3 item is produced, then in will point to the next location. So I think you have got it. What is in? Pointer to the next, pointer to first free location. I should say like this, pointer to first free location, that is in. What is out? Out is okay, let me tell you a few more points, then you will get automatically you will get clarity about what is out. Okay, so for example, consumer comes and consumer has consumed item 1. So obviously out will point to this location. Okay, and then I2 is also consumed by consumer. So now out will be placed here. Okay, yeah, by the way, in was not placed here. In is pointing to this location because here I3 was inserted. I think you have got it now. So now in is here and out is here. So what exactly out is doing? Out is pointing to the first field location. Please try to follow. Out is pointing to the first field location. Okay. So at the first field location, out is pointing. So see this, I1 was the first field location of which element was inserted first, I1. So it was the first field location. Out was pointing to the first field location. Okay, and when this item was deleted, see this, I2 was the second field location, I3 was the third field location. I2 was second because I1 was there. When I1 is consumed by consumer, then obviously I1 is deleted. So when I1 is deleted, so now what is our first field location? That is I2 only. Are you getting it? Now, see, there are three persons. So person A, person B, and person C. Okay, A is the first, B is second, C is third. When A is gone, obviously B is the first. When B is gone, obviously C is the first. So that is the scenario here. So out is always pointing to the first field location. When I1 is gone, I2 is the first. So out was pointing here. When I2 is gone, then I3 is the first. That's why out is pointing here and so on. I think you have got it. So in is pointing to the first field location. Out is pointing to the first field location. Okay. So now I think I have explained you counter is n means buffer is free. Sorry, buffer is full and counter is 0 means buffer is empty. So now see the producer code. What they are saying, repeat until false. See this, repeat until false. This is syntax of loop in Pascal. So they are saying dot 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 means what? There is some code and all. It is just a conceptual thing. Okay, it is not the exact program. It is just a conceptual thing. So they are saying you will write here the code to produce an item. Code to produce item. Okay, so I think they have not given something about next p. Next p you can think next produce. It is an you can say variable. Next p is a variable. Okay, and in that variable item produced will be stored by producer. Okay, next p is a variable to store item produced by producer. Okay, so next is a variable to store item produced by producer. So whatever item is produced by producer, it will be stored in next p variable. Okay, so you can just see, if you want to visualize, you can visualize it just like see this is a very big you can say some very big structure. Okay, so you can just imagine a factory environment, and in that factory this is a very big structure. You can consider it as a Almira or some very big machine, and this machine, these are the slots. So 1 2 3 4 and 5 slots are there. Okay, and another big machine has produced some very heavy item, so that item directly cannot be placed here. So what you will do, so you will take a trolley or something. Okay, in that trolley there are some wheels and all. So that item will be placed here first. Okay, so item is produced by a big machine, that is a producer machine, and this item is very heavy. So immediately after producing that item, you will place that in trolley, and by with the help of trolley you will take it and put it here and all. So that trolley is your next p, that is next produced. Okay, similarly consumer, for the consumer process, consumer is a very big machine and it want to consume some item, and items are very heavy. So we will take another trolley. Okay, so we will take another trolley, and in that trolley I will put that item. Okay, and I will give it to producer. Okay, so that trolley is next c. Next c, next is next consumed. Okay, next p means next produced. Next C is next consumed. Okay, so finally produce an item in next P. So item has been produced by producer in the next P. Now while counter is equal to n, do no op. No op means no operation. So when counter is n, that means what I have told you, buffer is full. So obviously first you have to check now. I think you have made programs in data structure algorithm about buffer insertion in queue, deletion in queue, and so on. So obviously first we have to check now. Whenever we are inserting some element, we will check that whether queue is empty, queue is full or not. So first our responsibility was to check whether queue is empty or not. Sorry, whether queue is full or not. Producer na, see, when we want to insert some element, then first we have to check whether queue is full or not. If queue is full, then you have to wait, otherwise you can insert the item. And when we are deleting some item from the queue, we have to check whether queue is already empty or not. If queue is already empty, then you have to wait, we cannot delete anything from the queue. Same scenario. Okay, so producer is producing item, that means it is inserting some element in the buffer, so we have to check whether queue is full or not. So while counter is equal to n, do no op. For counter is equal to n means buffer is full. Buffer is full. So when buffer is full, obviously it will create problem for us. Okay. Yes, if you are not able to see this, actually I have written buffer full. Yes, so I think you have got it. Nah? This means buffer is full. Yes. So now what I will say, while counter is equal to and do no, okay, we have done it. Now buffer in is equal to next p. So see this, I think you have got it. So where items are produced, whenever we are inserting some item in the queue, I have told you we have imagining a circular queue. Buffer here is a circular queue. So in was pointing to the next free location now. So at in only we are inserting item. So next item, say I4, I want to insert. I4 will be inserted at wherever in is pointing. So that's why I have told you buffer in is equal to next p. So item whichever is produced, it was placed in next p. So from next p, it will be stored in the buffer. So now this is important line. In is equal to in plus one mod n. See, who will increment the in whenever item is produced, then it will be incremented. So obviously producer will increment the in. But why we have written mod and see this? See, I4 has been placed here. See, in was pointing here and I4 has been placed. As soon as I4 has been placed here or I4 has been inserted, in will be pointing to the next free location. Next free location is this. Okay, now. So now, if we want to insert another element, for example, I5. So I have inserted I5 here. So now in will be pointing here. So now you can imagine if we keep on doing plus one, plus one, plus one, that will create problem. After four location, this is four location now. In will become five, but we do not want to make it five. We want to make it at zero. So that's why we are doing mod n. So you can check it out. So n is what number of elements now. So for example, here five elements are there. So I will say in plus one mod five. So 4 plus 1, we are at 4 location now. 4 plus 1 mod 5, that will be 0. So obviously after 4 we will come back to 0 and so on. I think you have got it. So to maintain the circular fashion, we have done n is equal to n plus 1 mod n. Okay, yes. So now counter will be incremented. Obviously counter will be incremented by producer. Why? Because it is producing item. And counter will be decremented by consumer because it will consume items and so on. I think you have got it. Please take snapshot. I will jump to the next slide. Yes. So here I have shown you the consumer process. So consumer process, see this, repeat until false. See this, repeat until false. That means loop, infinite loop. You can imagine it as an infinite loop. Same scenario here also, repeat until false. It is an infinite loop. Okay, now, so what we are saying, so while counter is equal to 0, no op. Okay, counter is equal to 0, no op means what? See, I have told you consumer will consume items now. So obviously it has to check whether buffer is empty or not. If buffer is empty, then it has to wait. So I have told you while counter is equal to 0, do no op. Okay, we will not do any operation. It will keep on waiting. Okay, next is, so next C is equal to buffer out. I have told you next consumed item, next consumed, that is buffer out. Okay, so I think you have got it. See this, out is pointing to the first field location now. So obviously element will be deleted from out. That's why I have written here. So buffer out. Okay, I think you have got it now. See, out was pointing to I1. So whenever I1 will be consumed, then out will be pointing to the next location and so on. I have told you now. So out is pointing to the first filled location. So obviously that location I have to consume. Okay, or content of that location I consumer will consume. So better is we will simply say buffer out. Okay, next is equal to buffer out. I think you have got it. Okay, so out is equal to out plus one mod n. Same scenario I have told you, circular fashion. In is equal to n plus one mod n. So here also out is equal to out plus one mod n. I think I should not give example. For example, when out is at here, so after 4, I don't want to make 5. I want to jump to 0 location. So for that I have done it. Out plus one mod n. Okay. Now counter is equal to counter minus 1. I think you have got it. Counter will be decremented. Why? Because consumer has consumed the item. Okay. So next is consume the item in next C. So these three dots means you will write code here. Okay. I have just shown you the concept. Proper code we will write how to do it and so on. Okay. Yes. So that's so now I think I have explained you the code of producer and consumer. So there is a very big problem here. Let me tell you that problem. So I think you have got it. If you have any doubt, please rewind the video and watch it again. Producer is producing item. So while counter is equal to 1, so first producer will see whether buffer is full or not. If buffer is full, then it has to wait. Otherwise, buffer in is equal to next P. So next, that means what item has been produced in next P now. So that item will be placed at buffer in. I think these are self-explanatory things. You already know. I should not repeat them again and again. It will waste our time. Okay, please take snapshot. Okay. Yes, take snapshot of this. Take snapshot of this. That's it. Okay. Yes. So next is the statements. The statements counter is equal to counter plus one, counter is equal to counter minus one must be executed atomically. That is the very, very important point. Okay, why it should be done atomically, let me tell you these things. Okay, and one more thing I want to say. See, I have told you that we are assuming that producer speed is more than consumer speed and so on. Okay, and see, whenever we have implemented the code, so you can think that producer speed actually should be more than consumer. If producer speed is less than consumer, then obviously we do not need the buffer and all. Okay, that is so obvious. Okay, but if in question they say that producer speed is less than consumer and still we have assumed a buffer and producer is producing item and storing them in buffer and so on, then we cannot fight with the examiner and all. The basic concept, the actual concept, I have told you that producer speed should be more than consumer. Okay, then only then this you can say bounded buffer problem is meaningful. Otherwise it is not at all meaningful. Why we are applying the buffer? Okay, when producer speed is less than consumer, or you can say consumer speed is more than producer, we do not need buffer at all. Okay, as soon as producer is produced item, it will be immediately consumed by consumer, and when their speed is equal, then also there is no buffer, no need of buffer. Okay, so buffer will be needed only when producer speed is more than consumer. Okay, I think you have got it. Okay, and if by chance, generally producer speed will be more than consumer, but if by chance producer speed has become less than consumer, or you can think that producer is slow. Okay, so buffer is needed when producer speed is more than consumer. But sometimes, see, no doubt producer is producing item at a very faster rate, but sometimes, or in some exceptional cases, producer will become slow. Okay, and in that case, I have told you, consumer will find that buffer is empty. Otherwise, you will say, sir, when producer speed is already more than consumer speed, then why we need this? Why consumer will say counter is equal to 0, do no op? That means what? Why consumer will find buffer is empty? Buffer will never be empty and so on. Okay, so sometimes producer may be slow also. So in that case, buffer will be empty. So consumer should not consume item at that time, because there is no item at all. How it will be consumed? Okay, and you can imagine like this also. Producer has produced say 5 items. Okay, and then see, these are actually processes now. Producer is a process, consumer is also a process. Okay, so after producing 5 items, interrupt came, and CPU has been given to consumer process. So you can imagine round robin scheduling and all. So now consumer is consuming items and so on. So it has consumed, say for example, more than if consumer wants to consume more than 5 items, producer has produced only 5 items. Producer has produced only 5 items and consumer want to consume more than 5 items, then obviously we have to check this statement. So while counter is equal to 0, no op, do no op. That is very, very necessary and very, very basic statement. When I used to teach in offline classes, many students have asked this doubt, that why counter is equal to 0, do no op, why this line is needed, because we have already assumed producer speed is more than consumer, so consumer will never find buffer to be empty and all. No, it may find sometime buffer to be empty. Okay, like producer has I think I have told you, I should not dig deep, because this is a basic course, that's all. Okay, yes, so there are many scenarios. So the basic thing is there are many scenarios, so that's why we have written this line. Okay, each and every line is necessary or very basic line in the code. Okay, yes, so next is that must be done atomically. Okay, what do you mean by atomically? Let me tell you. See, counter is equal to counter plus one. Actually, it cannot be done directly. Let me tell you what it how it will be done. So I will say MOV. See, this is a high level language statement, and it will be, you can say, converted into assembly language. Okay, so now I'm going to write assembly language code. MOV by compiler or interpreter, whatever we are using, it will be converted to assembly language. And that's why. So MOV R0 comma counter. Okay, so value of counter will be stored in R1. I will say INC R0. So R naught will be incremented. And then I will say MOV counter comma R naught. So value of R naught will be stored in counter. So these are the three statements which will be executed as a result of counter plus one. And whenever we, so this is only one statement, but actually when it is converted into assembly language code, it will be converted into three statements. Okay. Next is counter is equal to counter minus one. So let me tell you how it will be, you can say executed, or how it will be done in assembly language. So let me say step number 4, 5, and 6. So I will say MOV R naught comma, or let me take another, you can say register, because in R naught register we are doing this thing now. So let me take MOV R1 comma counter DEC. INC means increment, DEC means decrement. Decrement R1. And then I will say MOV counter comma R1. So content of R1 will be stored in counter. Okay. So atomically means I should not imagine interrupt while executing these statements. Okay, so these three statements, no doubt you may be imagining, sir, this is only one statement, but actually it has converted into three statements. So these three statements must be executed atomically. That means we cannot imagine interrupt and all while executing these statements. Similarly, while executing these statements, we cannot imagine interrupt and all. See, for example, if we try to imagine interrupt, that will create problem. Okay, so first of all, please tell me this thing. Counter is equal to counter plus one. Who is doing that? Who is doing that? Producer is doing that. Counter is equal to counter minus one. Who is doing that? Consumer is doing that. Now imagine producer and consumer both come at the same time. When they will come, when they both will come at the same time, then obviously problem will start. What will be the problem? See this. For example, producer has done till these two, you can say, lines have been executed, or these two statements have been executed, and interrupt comes, and then these two lines have been executed. Okay, these two lines have been executed. Okay, yes, and then interrupt come, then this line will be executed, and then interrupt come, then this line will be executed. So let me now try to build a scenario so that you get more clarity. So for example, counter value is 4. Counter is equal to 4. Okay, so now producer comes and then consumer comes. Producer comes, then counter will become 5, and then consumer comes, then counter will become 4. Obviously, now producer will increment it, consumer will decrement it. So finally, net value should be unchanged. So counter should be 4 only. Okay, one time producer come, one time consumer come. When producer come, then it will become 5. When consumer come, it will become 4. So it should not be affected. Or you can imagine another way also. When consumer comes, then it will become 3. Okay, when consumer comes, then it will become 3, because consumer has consumed item, and when producer will come, then it will become 4. So whatever may be the case, either producer comes first or consumer comes first, it hardly matters to me. Final answer will be 4 only. But what will be done here? Okay, imagine this thing. So uh, after line 2 interrupt come, or after statement 2 interrupt comes. So now please try to imagine counter value is 4. Let me write it here. Counter value is 4, and MOV R naught comma counter. So R naught has become 4. INC R naught has become 5. Okay, and then interrupt comes, and then here interrupt comes, and here these lines have been executed. So MOV R1 comma counter. Counter is still 4. Please try to imagine this thing. Counter is still 4. So R1 will get 4. R1 will get 4. DEC R1. R1 will be decremented and it will become 3. And now I'm assuming again interrupt comes, and control is shifted to this. So now MOV R naught comma counter. R naught value will be stored in counter. So counter will become 5. Counter will become 5. Okay, and when this will come, when after this line again interrupt comes, and then uh, consumer will start. Consumer will do what? R1 MOV R1 counter. So R1 value will be shifted to the counter. R1 is 3. So finally it will become 3. Are you getting it? So what we have done? One time producer comes and one time consumer comes. Value should be 4, but it has become 3. Are you getting it? So now you can imagine, like, see, these are just imaginary cases. You can imagine, and chances of happening is there now. Okay, so you can imagine like this also. After two lines interrupt come and this is executed completely. When this is executed completely, it will become 3. And when this line will be executed, it will become 5. Are you getting it? Let me show you. So this is the scenario. This is the scenario when we have executed line number 1, 2, 4, 5, 3, and 6. If this is if in this sequence these six statements are executed, final value will be 3. Okay, let me label it. Final value will be 3. But if we try to imagine a scenario where we have 1 2, after execution of 1 2, these are executed completely, 4 5 and 6, and then 3 is executed. Now please check what will be our answer. So after 1 2, let me draw it, no problem. So this is the counter. Okay, initially counter is 4, and we have to imagine R0 register and R1 register. This is R0, this is R1. So now 1 2. So R0, a counter value will be shifted to R0. INC R0. R0 has become 5. Now we have to execute line number 3, but before that 4 5 and 6 have been executed. MOV counter to R1. So 4. DEC R1 3, MOV counter R1, so it will be stored here 3. And when after that line number 3 will be executed, so R0 value will be shifted to the counter. So R0 value is 5. So finally value will be 5. So again it is wrong, na? Counter value was 4, one time producer and one time consumer. Answer should be 4. But here we are getting value 5. 5 is our final answer. So again this is wrong. So there are many problems here. Okay, so you can imagine scenarios and you can check it out yourself. So the basic thing is the process who has executed this statement last. Okay, that value will be our value. Are you getting it? So if MOV counter comma R not, that is executed in the end, so final value will be according to producer. That means 5. And when this line is executed in the end, then final value will be 3. Okay, if this line executed in the end, then final value will be 5, and when this line is executed in the end, final value will be 3. And both are wrong. That is the basic problem here. Okay, so I hope you have got it. So okay, and parallelly the things is parallelly we should do it. Okay, so if you imagine that 1 2 3 all are executed in the sequential order, then no problem at all. Why? Because counter will become 5 now. When producer come, then counter will become 5, and when this will come, it will read counter to be 5. Okay, so at that scenario there will be no problem at all. Are you getting it? So when these three lines are executed properly, then counter will become 5. And when counter has become 5, so now R1 will read counter to be 5. It will not read to be 4. So the problem is coming when both R not and R1 register, or when both R not and R1 register have seen counter value. Okay, and when they see the counter value, they will find it as 4, and that will create problems and all. That's why I have told you that producer and consumer should not access the buffer at the same time, because the moment they try to access the buffer at the same time, that will create problem, and this is one such problem. Okay, so I hope I have made the point clear to everybody. Yes. So here the problem is order of execution of instructions. Please try to follow this. Order of execution of instructions is giving us the actual value of counter. Actually, it should not be done like that. Order of instruction execution does not matter at all. Okay. So but here order of execution is defining the final result. So that is known as race condition. Let me jump to the next slide and I will write the statement. Take snapshot. I will jump to the next slide. Yes. So what is the race condition? First of all, please tell me when race condition will arise. When two or more processes want to access same shared variable at the same time. Counter is a shared variable. Producer process is accessing that and consumer is also accessing that. That is creating problem for us. Okay. So when two or more processes want to access variable at the same time, when two or more processes wants to access shared variable at the same time, shared variable at the same time, then race condition occurs. Then race condition comes, that is order of execution of instruction. That is order of execution of instruction defines the final value of variable. Defines the final value of variable. Actually, it should not be done like that. For example, counter value is 4 and one time producer come and one time consumer comes. Okay. One time producer and one time consumer. So it hardly matters whether producer comes first or consumer comes first. Producer will increment it, consumer will decrement it. So final value should be 4 only. But here we are getting problem and that is known as race condition. Please try to read it. When two or more processes wants to access shared variable at the same time, then race condition comes, that is order of execution of instruction define the final value of variable. I think you have got it. Okay, so now we want solution. Okay, so we want that these statements should be executed atomically. Atomically means one at a time. Okay, one at a time. Atomically means one at a time. So how we will do it? That is the biggest problem here. Okay, so we should say like this, that we should keep this counter variable. Counter is a shared variable, na? Counter is a shared variable. Why it is shared variable? Because both producer and consumer processes are seeing it and they are trying to access it. So these, whenever shared variables are accessed, they should not be accessed just like that only. For example, here we are not you can say written any code for locking and unlocking and so on. I'm just writing directly counter is counter -1 and here I am writing counter is equal to counter +1. Okay, so here we are accessing the shared variable. So these shared variables must be accessed in a special section of code that is known as critical section. Okay, so what is critical section? So critical section is nothing but a piece of code only. Okay, and here shared variables will be accessed. Are you getting it? So to access shared variables, we will use you can say a critical section. Okay, so critical section, let me write it. Every first okay, let me write it. Critical section. Critical section. So what I will say, need is need is what? See, our need is counter should not be accessed by both producer and consumer at the same time because it is a shared variable. So need is that counter that is shared variable must be kept in a special section of code called critical section. So please try to focus here. What is critical section? Critical section is nothing but it is a section of code where shared variables are accessed. Okay. So let me define it. What is a critical section? Section of code where shared variables are accessed. where shared variables are accessed. Okay, and each and every process has its own critical section. Each and every process has its own critical section. Okay, because it is section of code now, so each and every process has its own critical section. Okay, so I think you have got it. So what is the critical section for producer process? Okay, so for producer process, critical section is counter is equal to counter plus one. For consumer, critical section is counter is equal to counter minus one. Okay, yes, counter is equal to counter minus one. So that is the section of code, okay, where shared variables are accessed. Critical section is section of code where shared variables are accessed. Each and every process has its own critical section. So producer critical section is counter is equal to counter plus one. Consumer critical section is counter is equal to counter minus one. So when producer is doing counter is equal to counter plus one, at the same time consumer should not do counter is equal to counter minus one, because it will create problem, and final value of counter will be dependent on the order of execution of producer and consumer. Okay, it is not dependent on actually it should be independent na? Because when one time producer came, one time consumer came, I have told you, see, initial value is 4, counter value is 4. When one time producer, one time consumer, final value should be 4 only. It hardly matters whether producer comes first or consumer comes first. Okay, but here I have told you, see this, I have told you na, final value was either coming to be 3 or coming to be 5. Both were wrong. Okay, both were wrong. Okay, so whoever process has executed the line number 3 or line number 6 at the end, that will decide the value, and that is clearly race condition. Okay, I think you have got it. Please take snapshot. I will jump to the next slide. Okay, so now question arises, how to implement the critical section. How to implement critical section? That is the question which will come to our mind. Okay, so whatever implementation we are doing, so we should say like this. So, or whatever code is having critical section, how code should look like. Let me tell you this thing, and then I will show you how to implement the critical section and all. Okay, so by the way, how to implement critical section, that is known as critical section problem, CS problem. How to implement the critical section, that is known as critical section problem. Okay, but let me first tell you how code look likes. Okay, or you can say okay, let me write it, how code looks like. So see this. So first of all, we should have entry section. Then we should have critical section. And then we should have exit section. Okay. And then we have a remainder section. Okay. So whenever a code is having critical section, how code look likes? If it has CS implementation. Okay. In any code, if we have done critical section implementation, how code will look like? I will say there will be, say, 4 sections of code. First will be entry section, then critical section, exit section, and remainder section. Entry section, I think you have got it. See, this is very, very important. Here we will apply locks and all, so that when one process is in critical section, then other process should not enter that critical section. Because if 2 or more processes enter the critical section, then obviously race condition will come. And I have told you this thing, counter plus one, counter minus one. So when producer is doing counter plus one, then consumer should not come and do minus one. And when consumer is doing minus one, then producer should not come and do plus one, and so on. So these were the critical section for producer and consumer. So when producer is in its critical section, then consumer should not come into its critical section. Are you getting it? I am repeating again and again. Producer is having its own critical section. consumer is having its own critical section, and when producer is in its critical section, then consumer should not come into its own critical section. Are you getting it now? This is producer code and this is consumer code. So this is the critical section. So when producer process is in its critical section, then consumer process should not go into its own critical section. I think you have got it. Yes, so now see this. So how code look like? So first is entry section. So obviously when producer is in critical section, so it should have applied some lock here. Producer should have applied some lock here so that consumer cannot enter in its own critical section. See, because processes are different, their process address space is different. So obviously when one is in its critical section, then obviously second one can also enter. There are very high chances that another process also enter in its critical section. So better is producer should apply lock so that consumer cannot enter in its critical section. So this locking is done in the entry section. Okay. Yes. So entry section means locking. Then producer is in say critical section. When producer will come out of the critical section, then it will access this exit section. See this. When producer comes out of the critical section, like here, when producer is at here, then obviously since producer has applied lock so that consumer cannot enter. So now after coming out of the critical section, it should unlock. It should unlock this, because if it do unlocking, only then consumer can enter now. Because if producer forgot to unlock, then neither producer nor consumer both cannot enter the critical section, and that will create a very big mess for us. Okay, anyhow, I will tell you all these things in greater detail in the next lecture only. I'm just giving you an idea. So producer should unlock it. So that's why we have here exit section. So exit section will do unlocking. And what is the remainder section? It is no use for us. Okay, no use for CS. So it is just simple other code which we have written. Okay, just to see, we have done our we have written some code to do some task. So to do that task, we have this remainder section. Okay, for critical section, these three codes are important. For example, see this, we can think like this also in producer consumer problem. So this is the critical section. Okay, so before that we have some remainder section, and after that even we can have remainder section and all. So don't worry about it. I will tell you the more details in the next class. The only thing is remainder section is no use for us. For our current discussion, for our current context, remainder section is of no use. Why? Because in remainder section we will develop actual logic, that why we are doing programming and all. Okay, so like producer is producing item, so item will be produced and it will be stored in the next PC. This is all remainder section. Produce an item in next P and so on. So all this is remainder section. Okay, because that is not for us. That is the basic thing. Okay, or not related to the critical section. That is the remainder section. So I hope I have made the point clear to everybody. So these are the four sections. So now question arises how to implement the critical section, that is CS problem. Okay, that is the critical section problem. What is critical section problem? How to implement this critical section. Now we will see this. That means how we will apply lock, how we will apply unlock, and so on. So we will tell you all these things. Okay, but before that, we have to see how you will check that the critical section problem is good or not. Okay, or you can say solution. Rather, problem is the critical section problem only. We want to develop solution to the critical section problem. Now, that means how you will implement it. Are you getting it? Solution will tell us the way to implement the critical section. See, one is CS problem. Critical section problem is how to implement CS. How to implement CS. Okay. Next is solution to CS problem. Whatever solution you develop, that will be that solution will able to implement the CS properly. Solution to CS problem means so which can implement. Solution will implement. Solution means we will implement the CS. Solution means implementation of critical section. Are you getting it? So whatever solution we are able to design for the critical section problem, when can I say that solution is good? That is the question. Are you getting it? Critical section problem is how to implement the critical section. So solution to the CS problem means, solution means implementation. We have some implementation of critical section problem. Okay, I am giving you some solution to this problem. Problem is how you will implement it. So now I have done some implementation. When I have done some implementation, that will be our solution. So now when can I say solution is good? That is the question. Okay. So solution of CS problem good. When can I say solution to the CS problem is good? So I will say solution to the CS problem is good when it will fulfill three basic conditions. Okay. Solution to CS problem is good when following three conditions are fulfilled. Following three conditions are fulfilled. What are the conditions? The very first is mutual exclusion. Second is progress. Third is bounded weighting. Their definition is very, very important. If you are able to grasp the definition, then almost you can say 60 to 70% work is over. Then only we have to show you the solutions. Okay. So I hope I have made the point clear. So anyhow, definitions I will discuss in the next class. Okay. So now I think that's all for today. Okay. So we will resume our lecture in the next class. And the next class, I will tell you what are these three solutions to the critical section. So what are what are the three conditions which must be fulfilled? Okay. And after giving you the definition, I will jump to the solutions. So I will show you the solutions to the critical section problem. That means how I will show you the implementation. Okay. Solution means implementation of critical section. I will show you the implementations. I will, okay, don't worry. In the next class, we will resume the lecture. Okay. In the next class only, we will study these three conditions and we will discuss the solution and all. Yes. Please take snapshot. That's all for today. In the next class, we will resume it. Thank you so much. Bye-bye.